Ich brauche aber kein Mikrofon. Ne? Yeah. I'm the first one.
Okay, we need to put his phone on, his microphone.
That's for 3 minutes? Einfach drauf oder drauf oder nicht? We had a law kommt dann nicht das Ohr auf. So. Das heißt, dann hinter das Ohr so. Ah ja. So. Das kommt mir sicher vor wie ein Fernsehmoderator, oder? Ach du grüne Neune. So. Nein, ich mache keine Präsentation. Ich habe nur 3 Minuten eine Begrüßung vom Verkehrsministerium her und dann Finger in die Tasche. Gut. Das ist aber etwas irritierend, aber ist egal. Ja. Okay.
This is for the live stream. This is just for the room.
Okay. So. Ladies and gentlemen, dear guests, dear colleagues, on behalf of the Federal Minister of Transport, Building and Urban Development, Dr. Ramsauer, I'd like to welcome you warmly to the second day of the final conference of the ERA Net Road call, Road Owners Getting to Grips with Climate Change, here at the Federal Highway Research Institute in Bergisch Gladbach. Looking at the list of participants, I am delighted that so many international and national experts have got together to this event, organized by FAL in collaboration with BUST, and I hope the first day you have already gained valuable findings and recommendations. Ladies and gentlemen, the Ministry of Transport has been actively involved in ERANET Road from its beginning in 2005 and works very closely together with the BUST. The Federal Ministry provides the strategic direction, whereas the BUST performs the administration work in ERANET Road Consortium and the technical work in the program executive boards. This joint participation remains to be an interesting and very beneficial experience to all of us. Let me express my thanks to all members of the BUST who are engaged with high effort in ERANET Road, as well as to Mr. Bose and his team from the Federal Ministry. Ladies and gentlemen, as European countries, we are often faced with similar or even identical problems concerning road research. In the past, countries have done their own research in order to find answers to these problems, and unfortunately, countries have in many respects kept their research results to themselves. ERANET Road has now created a tool which allows us to do this research jointly. Through the methods developed by ERANET Road, we have been able to pool funds and to spend them transnationally, a practice which was unthinkable only several years before. This not only reduces the duplication of research, but also means the greater research results are available for smaller individual budget contributions. And with this, I hand over to Mr. Pechada from the Austrian Research Promotion Agency, who will give an introduction into the 4 projects from the climate change call. The results of the first transnational call will be presented here today, and we hope that these results will be of great value to you and ways may be found of how these can be implemented on national and European levels. I wish all participants a good meeting with fruitful discussions.
the first challenge, but let's stay ambitious. So also welcome everybody from my side. Thank you for the nice introduction. My name is Christian Pechada from the Austrian Research Promotion Agency. I think first of all I have maybe to apologize for my voice. It's not from the whiskey, but I have to fight the cold. But I think I will win the fight finally. I will give you now a short introduction to the program Road Owners Getting to Grips with Climate Change. It is a research program that was initiated by Eranet Road. Initiated by Eranet Road. What does that mean? So first of all, we need to know what is Eranet Road. Eranet Road, the first Eranet Road was a project, a coordination action from the 6th framework program from the Commission. It was from an idea from the CEDRA Technical Group Research. They asked who would like to join to do some coordination action. Some road directorates did join. It was 11 in this first Eranet Road. And the final goal of this Eranet Road was to improve the quality of results whilst reducing the costs, to create mechanisms to collaborate across borders, to achieve transnational programs which are strategically planned, transnationally funded, which leads to the mutual opening of national research programs, and to encourage the exchange of knowledge. And I would say the goals from Eranet Road were widely achieved. So for example, exchange for knowledge, an event like this, a workshop like this, is some kind of exchange of knowledge. We had a similar workshop 2 years ago when the 4 projects did start. It was in Oslo, a similar climate change conference. And all this was possible because Eranet Road did create a toolkit, the Eranet Road Toolkit, and there we have found procedures of coordination, a coordination procedure, and of management, a management procedure. And it goes like this. So first, when we discuss what could be interesting topics, which are high probable that many road directorates would join and give money for research actions. So we then organize a workshop when we found a topic. So in this first case, it was road owners getting to grips with climate change, with a workshop where experts could join and put in their ideas. What do road directors need in this topic? Then out of this workshop, we produced a description of research needs that was quite concrete. And on base of this description of research needs, and with the appointment of a program manager who will do all the operative work and administrative work around this program and the call, on this description of research need, on this base, we ask for commitment from partners. So they have to confirm the participation then. Those road directorates who would like to participate, they form a program executive board. Each directorate nominates 1 PEP member, and then when we have all the executive board operational, then we can open the call, and then the program executive board takes over to do the management of the call. So, and this is also the point where, when I said, when I introduced it, it was initiated by Eranet Road. That means Eranet Road prepared the mechanisms for the management and prepared the coordination. From that point on, it was not anymore Eranet Road, so there is no Eranet Road money in it, but from that point on, the program executive board, only the participating countries are involved. So we did the call, we got project proposals, then we had an evaluation process and the selection process that was developed by Eranet Road, of course, and the projects, they do run in accordance with the process that we described in the Eranet Road Toolkit. The first version of the Eranet Road Toolkit can be seen in the deliverable 4 of Eranet Road. You can find it on the website of Eranet Road. So then we have selected 4 projects. Each project was then supervised by 1 specific program executive board member. So we have a direct contact, personal contact between the project and the program executive board. Then for the monitoring, we have a process of 6 monthly progress reports that are given by the project to the executive board. And finally, we also have 6 monthly program executive board meetings to see if everything is on track and if the projects are running smoothly. So this is the basic output of Eranet Road 1, the coordination procedure and the management procedure. In Eranet Road 2, that was introduced yesterday by Patrick Maléchak, the coordinator of Eranet Road 2, we specify a bit more the coordination procedure and how we make it a permanent structure and how probably Cedric can take over, that this could be some instrument that can be used for transnational activities even after Eranet Road. So the first success in this story, the outcome of the Eranet Road 1, the first call that we did together was road owners getting to grips with climate change. The goal of this was to provide road administrations with tools to identify and prevent problems with road infrastructure due to climate change. So a road director needs some new knowledge to make a more efficient and better work of his daily work that he has to do, road maintenance, etc. And it was about risk analysis and risk management, climate impact on road infrastructure, mapping and classifying vulnerable structures, climate change scenarios, and adapting design rules and specifications. So this was more thoroughly described in the description of research needs, if you remember. Based on that, we did ask the road directorates who would like to join to do this call. And finally, we found 11 partners who were ready to give some money and who were interested to do some research here. And yeah, finally, it was the first cross-border funded joint program that we achieved, because there is no single European cent in this program. It's just the national money from these 11 funding partners putting together in one pot. Then we did make the call for proposals. It was open from March to May 2008. Finally, we got 19 proposals that were submitted from 18 different countries. So also on the researchers' side, there is exchange of knowledge and collaboration between the research institutes, and we do like to encourage this. And from these 19 proposals, we finally selected 4 projects with a total research budget of 1.2 million finally. So those 4 projects are the first projects that were initiated by Eranet Road. I hope you understand better now what that means. It was Swamp, Irvine, Rimorock, and P2R2C2. I will not tell you too much about the content because this will be the morning session now. You will get information about the results so far. Irvine already finished and the others are about to finish soon. We will listen this morning to the results. If there are urgent questions of understanding, then I might allow 1 or 2 after the presentations, but please make notes and keep your questions to the workshop session in the afternoon to have a fruitful discussion then. So we will like to concentrate now on the 4 projects and make notes. Afterwards, there will be discussion. And if you like to know the secret how we did achieve all what we have achieved now, it's simple. It's just all based on trust, understand, and commit. So what we did in Eranet Road was first to create trust between the partners. Then we tried to understand what the common goals are. Do we talk the same when we say something? And finally, we commit to it. This is a very long process, and sometimes I have the feeling that in the first program that we did, the commitment was based on trust, not with totally understanding what the procedures are. But meanwhile, we are here with complete trust, understand, and commit. And in January, we will launch the 4th joint call. So I thank you for your attention, and without much ado, I will give the floor to Bo Lind and Yves NSR, if that was correct pronounced. And for the first project, that's Rimarock. Bo, the floor is yours.
Thank you very much. Okay. Well, thank you very much, and it's a pleasure to be here in Köln to present the results from the Rimarock project. I'm from the Swedish Geotechnical Institute, and I'm doing the presentation together with my co-worker Yves from Egis in France. We will see. Are we ready? Okay, the old way. The goal, the purpose of the Rimarock project was to develop a common AeroNet road method for risk analysis and risk management for roads with regard to climate change in Europe. And as you can see, we were 4 partners, SGI in Sweden, the Egis from France, Deltares, the Netherlands, and also NGI from Norway. We had good support during the whole project from the program leader Håkan Nordlander at the Swedish Road Administration, and from the steering group with Åsa Lindgren from SRA, Geoff Rickert from Highway Agency, and Alberto Comte and Eva Ruiz Achiar from CEDES Spain. Then I will go straight to the point. What did we achieve? The Rimarock method consists of 7 steps. It starts with an overview context analysis where we set state what we are doing really. Are we looking at a bridge, a structure? Are we looking at a large area? Who is doing what? What is the organization about? And so on. And then we go through all these steps: risk identification, risk analysis, risk evaluation, risk mitigation, implementation of action plan, and finally monitoring, review, and capitalization, where we try to sum up what did we learn during this process. And this is, of course, an iterative process. You can see illustrated by the feedback loops, and you can also see the illustration with the green arrows, which illustrate the communication process with stakeholders outside this investigation or this theme. So we did not try to invent the wheel once again. This was based on, of course, the existing methodologies that we found. For instance, in the UK, which had already adopted a specific method for risk analysis due to climate change. We have also the JRC project in France. We have a method from the Netherlands. We have something from Sweden, from different countries concerning risk management for tunnels and so on. And so we just heard the presentation from Mexico. This is quite an ordinary process, and it is very formalized, and it is also very transparent, which means that you can go backward. You can always come back 10 years after, and you can find why did they take such a decision, why did they take such a measure. The proposed method is designed to be compatible and to operate in parallel with existing methods, just as I explained. It is also designed for all operational levels, from a specific structure, for instance, a bridge, to a large territory. It can be used, this method, for all these steps. There are really 5 documents to support the Rimarock method. The most important one is, number one, the guidebook to the Rimarock methods. I have them all here with me today, so you can have a quick look at them. And then we have 4 case studies from France, the Netherlands, Norway, and Sweden on different level, from a network level to a specific structure. And then if you have a specific interest in how we dealt with the design of this method, the function of it, we have a technical background report that describes a little bit of the working process and the seminars and discussions and so on that we had. In support to this method, we took the help from climatologists, experts from France, the Netherlands, and Sweden in defining the critical climate parameters. And from a long list, from seminars during a value engineering process, we came up with these ones: extreme rainfall events, long seasonal rainfall, sea level rise, drought, snowfall, etc. That we find are the most critical parameters. In addition, we made some definitions for each of these climate parameters, their influence on the infrastructure. Example, rainfall events, flooding, erosion, overloading of drainage systems, and so on for each event. And also, in addition, for each of these climate parameters, you can find in the handbook weighting according to the importance for the road sector, from 1 to 4. 1 is a parameter which we find useful but not very critical, and of course number 4 is very important, critical, or of primary importance. And then we also have the amount of change that we expect from these climate parameters, from significant increase plus to decrease minus. And here we use also the definitions from the IPCC, which is likely, very likely, virtually certain, and so on. And this tool you can find as a help in the Rimarock handbook. So this is how the handbook looks like on the left-hand side, and it is divided into 3 parts. The first part is a general description of climate change impact on the road system and a general presentation of risk management. And then we have part 2, which is actually a structural guide through this method. And then we have a short description also of these 4 case studies. And at this point, I leave the floor to you, Yves, and even this one. Good luck.
Thanks. Thank you, Bo. No, it's okay. So, yes, my presentation will focus on part 2, the method, and I will give some illustration of each steps of the Rimarock method based on case studies. So, as Bolind told you, the Rimarock framework consists of 7 steps, each with a number of sub-steps. All steps are presented in the same way, starting with a summary of the step and a list of the sub-steps. The sub-steps are structured as follows: objectives, output, method, the data collected, and examples. What I'd like to say at the present stage of the presentation is that you may consider that some sub-steps that I will present you are optional or less important than others. As a matter of fact, that's the way we implemented the Rimarock method. Each partner, when performing the case studies, we decided to merge some sub-steps or to give more importance to of some sub-steps. So it's just to say that the Rimarock method is flexible and you can adapt it to specific context and needs. So the first step is about context analysis. By establishing the context, the authority responsible for the climate risk management study articulates its objectives, defines the external and internal parameters to be taken into account when managing risk, and sets the scope and risk criteria for the remaining process, and of course define the nature and the extent of the study area. So sub-steps are establish a general context, establish a specific context for a particular scale of analysis, and establish risk criteria and indicators adapted to each particular scale of analysis. This means that the first step is common to every scale of analysis, but the other, as we can see on the following slide, may be specific to the case study. And in this case study concerns the northern French motorway network. You can see the motorway network operated by the SANEF concessionary company. It is about 1,000 kilometers of motorway, and corresponding to about 40 motorway sections. And when defining the specific context of this motorway network, for example, we paid attention to the components structuring or strategic elements of the territory that could be taken into account in the general analysis of the context, such as, for instance, the main industrial areas, the main regional hospitals, the main airports and ports, even the nuclear power plants, and so on. So this is an example of context analysis. In the third sub-step of context analysis is about risk criteria and indicators. In this step, in this sub-step, the aim is to start defining what are the main indicators of climate factors exposure, vulnerability, and climate risk consequences. This example is on criteria for assessing exposure, taken from the Norwegian case study on road section. You can see four different criteria that are ranked according to four level of values, from low criticity to high criticity. As far as possible, we try to quantify the values of the criteria, but sometimes it's not possible, and only a qualitative appraisal can be carried out. So the second step is on risk identification. The risk manager should identify sources of risk, areas of impact, unwanted events, and their causes and potential consequences. The aim of this step is to generate a comprehensive list of risks based on events that might stop, degrade, or delay the normal operation of the road system, or create trouble or damage in the exposed area. The sub-steps are proposed in relation to the risk definition, and the risk definition considered in the RIMARC framework is a combination of threat, vulnerabilities, and consequences. So to illustrate this step, I will show you how we identify vulnerabilities on the northern motorway network in France. So during a brainstorming meeting with the concessionary company experts, we identified some criteria that can be used on the 40 sections of the network. And so these are these criteria. First, the length of the section, the age and corresponding design standards, traffic amount, the sensitive elements in the infrastructure, but also outside the infrastructure in the surrounding environment, and the climatic factors likely to affect the sensitive elements of the infrastructure, such as, for instance, for the first section, extreme rainfall likely to cause overflows for more than 10 years return period flood, and taking due account of possible aggravation indicators related to climate change. And thanks to Météo France expertise, we were able to forecast some additional flow for the 2050 horizon, and so it shows that the present situation can get worse in the future according to this parameter. But of course, there may be other climatic factors involved, such as extreme wind speeds or average number of frost. And so that's the way we did for the 40 sections of this network. On step 3, the objectives of risk analysis has been defined as to develop an understanding of the risks. The risk analysis provides input to risk evaluation and serves as a decision basis for whether risks need to be treated and for selecting the most appropriate risk treatment strategies and methods. And sub-steps are establish risk chronology and scenarios, determine the impact of risk, evaluate occurrences, and provide a risk overview. So I will leave the floor.
It's a little bit complicated. Yes. Can I just hold it like a microphone? Hopefully, yes. Well, this is just a way of scoring the consequence indicators. On the left-hand side, you have the 4 scenarios from the Swedish case study: extreme flooding, extreme rainfall event, and flooding of the road, or even a collapse of a nearby dam. And then you have the probability of the risk, which is a combination of the climate event and the road event. And then you have the scoring of the consequence criteria: exposures, sensitivity, and consequences. And this is a way of illustrating how severe we feel that each of these indicators are in this specific case study. Well, I think I will stop there.
So the fourth step is about risk evaluation. The objectives of risk evaluation is to assist the risk manager in making decisions based on the outcome of the risk analysis about which risks need treatment and the priorities for treatment implementation. Risk evaluation involves comparing the level of risk found during the analysis process with risk criteria established when the context was considered. Based on this comparison, the need for treatment can be considered. Sub-steps are risk prioritization, compare climate risk to other kinds of risk, and determine which risks are acceptable. And so, once again, the example will be clarified by Bo.
Yes, this is also from the Swedish case study, and now we are going to get a little bit more concrete. This is, of course, one way of presenting the result from the risk evaluation. On the horizontal axis, you have the consequences. On the vertical axis, the probability. And here you can see the 4 scenarios from the Swedish case studies. And in this case, we have presented them with arrows. So this means that the position in this matrix is the position of today, the today situation, and the arrow means in which direction we expect these scenarios to move according to climate change. Another way perhaps could be to make a matrix for today's situation, and another matrix where we put in these scenarios in 20 years, in 50 years, and 80 years, and so on. But in this case study, we just choose to show the arrows to point out the direction where they are moving. So you can see one of the scenarios is expected to be less probable due to less snow and less snow melt, actually. But I won't explain the scenarios exactly. They are of course in the case study report. Thank you.
So the 5th step is about risk mitigation. Risk mitigation involves identifying, appraising, and selecting one or more options for modifying the non-acceptable risks. A combination of the identified measures can be transformed into a strategy for the coming years in order to cope with climate change and keep risks acceptable. This step also includes securing financing as well as documenting in an action plan how the chosen adaptation measures will be implemented. Risk mitigation is a strategic step which may involve players from several departments: roads, civil security, finance, and others. Sub-steps are identify options, appraise options, negotiation with funding agencies, and present an action plan. And I will give you an overview of a possible method on mitigation option appraisal, taken from the Dutch case study from Deltares. So, as you can see, there are some usual appraisal criteria, such as the cost, estimated cost, that can be used to distinguish, to rank the 9 adaptation measures compared in this example. You can also, of course, compare these adaptation measures regarding their effectiveness on consequences, on risk, on climate risks, on I mean their effectiveness regarding how they deal with climate risk mitigation or adaptation. And the third criteria, which may be more specific to climate change, is the way these various measures can be classified according to the time scale of their effectiveness. Because some of the adaptation measures can be effective as soon as possible, right now, maybe, for the present situation. Usually we call them no-regret strategies because they can work, they are effective with or without climate change. But some other adaptation measures may not be effective right now, but in a few years or in 20 or 50 years, and so with such delay. And so this is important to keep in mind when building a strategy on climate change adaptation. So we will talk a little bit on the last two steps of the method. The sixth one is about the implementation of action plan. In this step, the action plan is presented in detail. Responsibilities for implementation are addressed. Resources are allocated. Performance measures are selected. When all the details are in place, the action plan is implemented. This is a strategic step which involves players from several departments, roads, civil security, finance, etc. Network and territorial scale analysis require information on which geographical units of the organization should be involved. This also applies to stakeholders' contacts. The two steps are develop an action plan on each level of responsibility and implement an adaptation action plan. And the last step is about monitoring, review, and capitalization. So since risk management is a learning process, this step aims to monitor and review the implemented actions and to capitalize the knowledge gained within climate events and the implementation of action plans. If conditions change, replanning starts within this step. Sub-steps are regular monitoring and review, replan in case of new data or a delay in implementation, and capitalization of return of experience on both climatic events and progress of implementation. Thank you.
Well, thank you very much. Are there some urgent questions of understanding, or have you just made notes for the afternoon? That would be the preferred option. So I will introduce now Pirkko Sarikivi from the Irvine project, Improved Local Winter Index to assess maintenance needs and adaptation costs in climate change scenarios. So maybe a project that fits with the weather today. So Pirkko, the floor is yours.
Thank you. Yeah.
I will tell you 5 minutes.
Yeah, okay, this is not so long. Okay, everybody, ladies and gentlemen, I'm really happy to be here today and see so many of you, and unfortunately, weather actually prevented me coming here yesterday because I was sitting at several airports all day long, and if there is something in my presentation that you already heard yesterday, I'm sorry, but anyway, the issue is so important that repetition is just good. Irvine project, where do I change this, by the way? Yeah. The title, Improved Local Winter Index. Our aim was to do that, to assess maintenance needs and adaptation costs in climate change scenarios. That is our topic today. And it was a project that is now already completed. It took about 1 year. And we had 3 partners. This was truly a Northern European project with partners from Finland and Sweden. I'm the managing director of Forerka Consulting in Finland. I was the coordinator. I'm a meteorologist and also road weather coordinator in Finland, being a contact to our road administration. And then we have Klimator AB. Torbjörn Gustafsson, professor, is also here today and will be with me in the workshop in the afternoon. And then University of Gothenburg Regional Climate Group, they did all these climate simulations. And the idea was really for the first time, really to analyze very carefully all road weather observations in Finland and Sweden that had been archived. And the idea was really to now do some climate scenarios that have been really downscaled to the local road network using these road weather observations. And in this way, we really would know what is going to happen on the road network in detail, and then try to compute these new, more accurate winter indexes. But first of all, this background information, I have to quite often convince general people, general media and laymen that yes, climate change hasn't been cancelled, because last winter in Finland was extremely cold, and this winter as well, and also in Central Europe. And it's always hard to convince that yes, this is local change, but in global perspective, really the trend is extremely alarming. These values come from NOAA, and they are really updated. They update their website constantly, and I just updated these figures as well. And this year, which is the last blue dot, these are annual mean global values, is the guess of this year's result, which is almost there. And it seems that if not the very warmest, it is one of the most warmest years ever observed with present technology on this globe. And something really horrible started to happen in about 1976 after that, because after that really no values below normal value of 1951 and 1980 have occurred, and the trend is really very, very positive. Those purple values are 5-year running averages, and they really are going up fast. And then if we take a more closer look, this is now only 16 last years, but now monthly average values in temperature, global temperature. You can, of course, see more variation. You can still see the positive trend. But what is interesting are these extremely warm months. You can see 4 of them in this last 16 years. And they always happen to be wintertime months in the northern hemisphere. There is one February, March, January, and another March. This year's March was one of those. So this also indicates that the wintertime weather in our areas in Europe may have really some very, very extreme phenomena. Climate models have been built for many decades now, and they have been, of course, improved a lot during these years while I have been in the area as well. And the physics is now much better resolved, but still the resolution of the global models could be better. Of course, the computing resources you need are enormous, and you just cannot have compute the models as accurately as you want it. So this is one problem when we want to mirror the climate models to the road network. The raw values that you get while running the models are not really accurate enough. And that's why we are having this other method I will explain you soon. Well, the other matter that is really controversial, and there is a lot of debate about this, is what is actually the scenario, because it depends on our emissions. I think more or less all scientists today, they really believe and know that this global change is due to increased anthropogenic emissions and CO2 and other greenhouse gases. And of course there are other effects like sun and so on, but they are minor. But what is now the speed? And most studies use this quite positive scenario A1b, which is the green line in this picture, which tells that yes, we have the growing trend for the coming years, but then finally in the end humankind will come to their senses and the emissions start going not so fast. Well, personally I don't believe this. I think we go even faster. So even though in our study we use this A1b scenario, of course this may indicate that actually we have more extremes coming in the future than what we are showing in our figures. But of course it's good to be optimistic. Of course there are many good projects going on now to reduce the emissions globally. Well, this picture is something I already saw something like this in 1970s while I was a student, and my professor Eero Holopainen showed us that time climate models, which are of course not at all as good as they are today. But still the picture was exactly the same. I remember it so well, because the picture, even then we heard that the northern latitudes will feel the most of this new burden. They will really warm up much faster than the other globe, of course. Everywhere this is a problem. And the values in the northern, where we are there up in the north, can be even 5 degrees or more till the end of this century. And this is of course due to the positive feedback effects from the ice cap and so on. So no wonder that we see those very alarming months that are extremely warm in the northern winters. Well, then to our method, downscaling. This really means that we are using the best climate models we have today, but we are trying then to refine the results using better local observations. And the key issue here really is to find the best meteorological observations. And then to do this downscaling, it's not enough to use just 1 year. We should have enough years that really reflect all kinds of local phenomena. The quality of the data must be as good as possible. All observation errors will be bad because they will decrease the quality. Then we should have uninterrupted series of observations, and the stations should be more or less on the same locations. And we should know if there are any changes in the equipment and so on. Well, what we used is what we think really the best possible source for road weather observations, and that is the road weather information systems that have been installed in Sweden and Finland and run under the National Road Administrations. And their local representativeness and the resolution is so much better compared to a normal weather network. That triangle there is just one meteorological station in Göteborg, Gothenburg area, but all those red spots are road weather stations. So in a small area you can have 10 or even 20 stations compared just to one meteorological station. So you understand that indeed this is a good candidate to do the downscaling. Other advantages are that these measurements are really done just close to the road, so they reflect the road climatology. And this is the data that the maintenance people are really using while they do their decisions. Also, the measurement frequency is very good, usually half an hour or even shorter. And then really there are so many much more stations than the regular network. So we started to look at this data, and we selected small areas in Sweden and Finland that would reflect different kind of local climate. And in Sweden, these are now marked from S1 to S3 and go from southwest to northeast. So S1 is the most warmest in climate in Gothenburg area, S2 is Stockholm, which is colder, and S3 is even colder in Sundsvall. And S1 Gothenburg area is also windiest because it is receiving heavy winds from the sea area. And in Finland, similar structure, F1 in southwest, which is the warmest, and F2 is in the east. It is already feeling the continental climate from Russia and Siberia very often, and F3 is the so-called snow Finland, where really it's continental, a lot of snowfall. Unfortunately, we wanted to have, the station network is there, we wanted to have an area in Lapland, but we soon realized that there is not enough data to have that, so we had to rely on this F3 as the most coldest area in our study. So some details from our Finnish database. We analyzed all data available. It starts from 1997, and we had about 10, 11 years. And during this period, station number has increased from 2,500 to more than 500 in Finland. In Sweden, there are even more, I think 600 to 700 stations at the moment. And while we went through the data, we really selected the best ones, and we selected only about 50 time series. So they were the best, uninterrupted and so on. And they had all these basic parameters. And then we selected, we are now looking at only winter months from November to March. We don't care about summer because that's not valid for this study. We also collected maintenance and salting information, how many maintenance actions had been during those years, but unfortunately this information was available only from 2003 onwards, so it was a little bit shorter. Well, what is then the winter index? This index tries to tell what is the risk due to weather to have a certain maintenance action. And the weather parameters are due to the risk of slipperiness, which can be due to many different parameters, and also if the snow is falling, if there is precipitation. And then we have to know the temperature, if it's close to zero or not, and also the wind, if it's heavy or not. So these are the basic parameters we are looking at. So this is how we did everything. We had first road weather information system database. We did that first. We had to really do a lot of quality control for the data, but once that was done, then we were running the climate models and had the climate database. And that was reflected to 2025 period, so it was about 30, 40 years ahead in the future. And using this one, then we did the climate index calculations, and once we had those, we were able to even calculate some adaptation costs and analyze those. This is unfortunately very small text, but it just tells what was included in the 9 indexes we calculated. There was first 6 ones were dealing with plowing risk, so the snow was falling, what was the temperature, how much wind, and then the 3 last ones were salting risks, different kind of weather risks that require that maintenance action. And these are now the results from the salting indexes, the 3 ones, and these areas in Sweden and Finland. Well, you can see that most of the percentages here are positive. Only in Gothenburg area, salting should be less, and a little bit in some cases in Stockholm area and southwest Finland, but everywhere else more salting is needed, and quite considerably, especially in northern areas. And this is quite natural result, because the temperature due to warming climate will be more often close to zero in those areas than it is nowadays or used to be. And then ploughing, again, quite natural results, because climate change is progressing. There is less snowfall expected, especially in southern Sweden. There are some cases with considerably less ploughing needed in this scenario. And, but some positive figures as well, especially in the first column you can see. And this is now due to the fact that in a very cold climate there is snowfall, but the amounts are less because the atmosphere is cold. When it's getting warmer, actually we are getting more and more frequent snowfalls. So this is in some areas causing more need for ploughing. Here is just different snowfall events with either small amounts or more amounts, and here you can see the same effect. These small snowfalls will get less, but then these events with a lot of snowfall we will get more frequent in northern Finland especially, but less in those more southern areas. Then if we calculate from the maintenance information what this actually means in maintenance kilometers required, this is now only for area Gothenburg area in southern Sweden, we can see that yes, there indeed much less kilometers are needed annually to do the maintenance, simply because you don't have to do it. And finally, you can do this even in more detail. With some statistical analysis, you know how the local roads are, how their maintenance needs are, and you can, using these downscaled values, you can do even more accurate analysis on the local network and calculate what this actually means in different roads and different type of roads with different maintenance requirements. So even this kind of analysis is possible and very useful. Okay, then our summary of our results. First of all, advice to road owners. We think that this road weather information, because it's collected in most of the countries, especially in those countries with wintertime problems, it is really valuable information. All of that should be archived in as good format as possible. And keep the numbering of the stations unchanged and good metadata existing. And because this really could be used also in other countries for climate studies. But before doing that, there is some work to be done. The data should be interpolated in equal time steps, really, to do any decent work. So this would be, of course, another burden to road owners, but a really valuable one to do that. Benefits were that we had, after this work, a better linkage between weather and maintenance needs. We understood the variations better that are expected in the changing climate, and understood better the impact of climate change to maintenance needs, and something also about the extreme events. Our final report is available from Eranet Road website. There is the title. Also, there are some these annual reports. If you are interested in the very details, those are also available. Thank you.
So thank you very much, Pirkko. And as you mentioned, maybe as an information for everybody, all the reports, the final reports that are approved by the Program Executive Board, they will finally be published and be available on the website. So if you regularly check the Aeronet Road website, then you can find the reports that we have so far and can see if you could use it in your own road administrations. So the next projects that we'll get some information will be SWAMP, the stormwater prevention methods to predict damage from the water stream in and near road pavements and lowland areas. And we will get this presentation by Michael Larsen from the Danish Road Institute. Michael, the floor is yours.
Yeah.
As soon as the cable is on.
Is the cable on?
It is.
Okay. First of all, I have to apologize for my English. I am Danish, if you haven't noticed, and I'm trying to speak English. That's usually, this combination is usually called Danish, so I have to apologize. The project we are going to present, me and my colleague from Sweden, is the SWAMP project. We have page down. Yeah. And as Christian just told you, it's an acronym for stormwater prevention methods to predict flooding from roads, from water stream, I can't even remember the title, and in near road pavement in lowland areas. The partners in the project. We are two partners, the VTI, or Swedish National Road and Transport Research Institute, 3 persons from VTI, and Frederik is here to present the other part, and Danish Road Institute. And we have a consultant, which we have to thank very much to bring the GIS model alive. It's PH Consult in Denmark. The frame of the project is in 3 parts. We have a background. First of all, we have to study some literature to have some data collection about climate change models, how reliable are they, and we have sent out a questionnaire to ask road administrations if they have experience with flooding, if they already have a GIS model. We will not kick in open doors, and if they have any experience in other ways with flooding of roads. Then we have the second part. The blue spot model is actually the more technical part in developing the GIS model for predicting, for forecasting all the blue spots on the roads. And when we have pointed out all blue spots on the road, we want to make a guideline to how to inspect and maintenance all these blue spots. And that's the third part. And my colleague will present a little more about the inspection and maintenance when I'm finished. I will move on to the blue spot model and jump right to the points. We have these 2 days seen a lot of challenges for the roads and road owners. And we have a great challenge in renovation and maintenance, the existing systems. The capacity of our detention basin has decreased because of sedimentations. And the next bullet makes it worth more, because we have further regulation from the EU in the Water Frame Directive telling us that we must not discharge so much water from our detention points into the environment. So we have a decrease of water, and we have an increase of water from the climate change. So we have a lot of challenge. Gives us all an increased risk of flooding of roads and infrastructure. We have some solutions. Increase the storage capacity. It's almost in economic way, it's getting more and more expensive down the road. Improve the function of the system. We can install pumps in lowland areas. We can even regulate the terrain. And the most expensive one is moved exposed roads. But where do we start and how do we prioritize? We have tried to do it in a mapping way, making a GIS system for blue spot identification, and now you got our little definition of what is a blue spot. We have tried this GIS model in Denmark. In the red frame, we have a demonstration project. It is based on a terrain model which is based on a laser scanning. This laser scanning makes it very accuracy for the elevation model. The elevation model in this area have a resolution of 10 centimeters to 25 centimeters. So we have a 10 times better map in a digital form than the old analog. Our model is in 3 levels. Each level gives more and more information down the road. The first level is screening of the terrain data, completely identifying all the blue spots in the area, finding all the lowland, all the hollows in the area. Second is how much rain will it take to fill this blue spot. And the third one is a more sophisticated one. When you have pointed out all the severe blue spots, we can use models, hydrodynamic models, to calculate more accurate how it will react on a precipitations. First level, screening all data, the terrain data, and identify all the blue spots. This, as you can see, is a blue spot map. And if you notice this area, we have may have a problem in this area. It is a junction of a highway system. Moving on to the next step is calculating how much rain it will take to fill this hollow in the underpasses. Now you can see it's green, and the legend tells us that it takes over 100 millimeters in 24 hours to fill this underpass. And we have presumed that all the catchment area is 20% impermeable. It's quite normal in a dry seasons. But please notice this area. When I make the catchment area 100% impermeable, my blue spot turns orange. And orange tells me that it only takes 26 to 50 millimeters in 24 hours to fill this junction. It's quite normal precipitation in Denmark in 24 hours. And you can ask, 100% impermeable, when will it happen? Well, it will happen if all the catchment area is saturated from a long time rain, or if we have a frozen ground. The third level is a more sophisticated level. We have to analyze with hydrodynamic models. We can calculate all the small parts contributing to the blue spot. Finding out in a certain event, this is a 100-year storm event, the water level beneath the bridge and in the underpasses. This is a little more sophisticated. I won't go into details now. In the same way, we can use the model to predict sea level rise. We have a town close to the sea, and if we let the sea level rise with 1 meter, and we can let it rise with 2 meters. Now we got some roads on the water. We can also exaggerate, give it 3 meters. We've got a whole town underwater now. In this way, we can predict sea level rise near exposed roads. Rising water level in rivers is also possible. In a normal situation, we have a river going under 2 motorway systems. If in a heavy rain situation and we got a plug in that, we can, on the basis of the catchment area, the duration of the rain time, the rain period, and discharge, we can calculate the water level of the river at any time. And now for the prioritization. We can use Rimarock, as Bo Klinger-Eaves presented. I have condensed it a little with the probability and the consequences. Every blue spots can, use Rimarock, be put in this matrix, and then you can prioritize which blue spot you want to take first. And of course, we have some recommendations for drone owners. Of course, we recommend that you are using this predicting methods. It's cheap, it's easy to use, I think. And what we have been used in this project is what we call nice to have. We have a laser scanning with this occurrence. We have aerial photos to check the laser scanning. We have technical map with roads and houses, databases with information on bridges, river crossings, and etc. And we have used an ArcGIS desktop program. And for the hydrodynamic models, we have used Mike Urban and Mike Mouse as a software from Danish Hydrological Institute. This is nice to have. What you need to have is at least map in digital form with elevation curves. So further on, you can use Google Earth. You can use also Google Earth to produce technical maps, and Google Earth to create databases with information on river crossings. MapInfo for GIS is okay, expensive, but there are open sources for free on the internet to do the GIS calculations. And if you want to move the third level, there are other models, hydrodynamic models from Deltares and Wallingford and Tuflow. So this is recommendations. And to summarize, we have a 3-level GIS model pointing out all blue spots. We can make a risk analysis using Rimarock as a 4th level. And finally, we can use the second part or the third part of the Swarm project inspection and maintenance, where we can, after pointing out in the risk model, we can use the maintenance and inspection methods and guidelines to maintenance the single blue spots you want to maintenance. And now I will leave the floor for my colleague.
Still the same project?
Still the same project.
Yeah. Thank you.
Yeah. Hello. Yeah. Yes. Just. Hello. I'm sorry that it's my fault that it was 2 presentations. I was a little bit late with my presentation preparedness. So, otherwise we had quite a nice collaboration in this project. So it's not like it looks like. It's not 2 projects in one. The content of this presentation is going to be about the strategies to prevent flooding of roads, inspection and maintenance of road constructions. And it was one part of the project. As you heard many times here today, climate change will increase the risk for flooding. This EPCC model clearly, see how this works? Yeah. Clearly shows that you have, even if you choose a moderate scenario here, you're going to have an increase in the global temperature. So that will increase the risk for flooding. But the present climate also gives problems, as you have seen today. For example, the Mexican example was very illustrative for that things happening. And also smaller things, floodings happening. So it's very good to look over this kind of maintenance and inspections of roads. We also have an increased demands on the infrastructure. People want better communication, less stops and faster and better comfort on the roads. We don't want to pollute the water quality. So, and people are actually needs better communication to be able to do their work, and that's how the society develops. And also we have the roads. It's a long-term investment, so the roads are normally based on the design on the roads on a previous climate that are based on experience in the past. And we also have, with this the financial crisis, you get less money for maintenance and inspections. So it's also a challenge to do more work with less money. And as you all know, water is perhaps the most detrimental thing to road constructions and shorten their expected service life. In this part of the project, we have looked into inspections and maintenance. The aim was to provide guidance and information about flooding of roads to road owners and managers, and prevent them with what kind of information they might need. Also inspire to new routines for inspections and maintenance, and develop their old ones, and highlight the importance to maintain their drainage system to prevent flooding. We started the work with sending out a questionnaire, and it was sent out to the ERANET countries to assemble their experiences, and from professionals working with drainage and flooding. If you look in the mirror, it might was a little too ambitious. When you're doing questionnaires, I've learned that it's very important to condense them, short ones, and because we're sending these questionnaires to very busy people. And the other thing we wanted to do with the questionnaire was to identify if there was manuals or working procedure for inspections in the maintenance area. The results came back from 17 answers and 11 countries. And the main conclusions from this questionnaire was that it is actually a great need to identify and prioritize roads sensitive to flooding. All these people felt that almost all answers came back that it's a great need for doing this work. It's a need to develop strategies for inspection and maintenance, and many road administrations has also started doing that. And it's also apparent that inspection and maintenance have often quite low priority and lack of money. Also, one other conclusion is that inspection and maintenance strategies differs in different countries. Of course, that's natural because they have different conditions, climate, geology, and different needs from the society, and also, to some sense, different type of constructions. So there is different ways to do this kind of work. We realize that therefore it's quite hard to suggest a guideline that works generally in all countries. So we didn't manage to do that. Here a little bit about the basic strategy. We think that it's important to follow a certain strategy, and the first step in this strategy is to find the most vulnerable road sections to flooding, preferably with the blue spot mapping that Michael has showed you before. And but there is other ways also to do it. And then prioritize with risk management, like the RIMAROC project suggestions, and then do the maintenance where it's most needed, and then after that upgrade and renovate the most sensitive places if you need that. When you have done your homework with your risk management and found this road section that's vulnerable to flooding, you need to collect some background data. And we have 4 steps here. Evaluation of the drainage system, their design, capacity and function, maintenance and inspection routines, and their look over these and develop new ones so you can so you know exactly what to do on these places, and perhaps also install early warning systems. The general information you need are listed, a few of them, like maps, different types of maps, streams, lakes, and also what from the blue spot mapping you get the catchment area, what area is actually contributing to this particular blue spot area. Where can you expect the water to come from? What kind of terrain and soil you have on the place? Road type and where? Population density and that kind of things. And its construction and design. And also this is very important to also learn from the past. Look into what has happened to this particular place before. Has it experienced flooding before? Have you done some repair works? How is maintenance inspections doing on this place? And then you need to look into the drainage system and analyze that. You have to understand what type of and design you have. If you have retention ponds, is it possible to get rid of water somewhere in the system? It can be, for example, a field or something that you can have as a place to get rid of the water that's coming. Design and rainfall capacity. How much flow is it? Is a system capable of taking? And how much flow can you actually allow to go into the system? In some cases, it might be better to have flooding early than putting more water into a system and then get lots of problems downstream. And then we have the routines. For example, the inspection and maintenance activities. You want to decrease the risk for flooding. Normally, this kind of inspection and maintenance activities include cleaning and mowing of vegetation and test of function. And we think it's important to at least on these places have annual inspections. And in some places it might be even better to, not better, but also include extreme weather inspections. So you do a sort of inspection before you know you have a large rainfall coming in, and see that the system are well functioning and not lots of garbage and stuff that's plugging the drainage. And also perhaps look when you get this rain into the system, during the raining and whatever event, check what's happening. Is it and look if you can learn something from that happening. And also very important after the event, try to inspect the damages. You can read a little more about that in the report. This is just this condensed information here today. And then in certain places where it might be worthwhile having a warning system. It can be connected to weather alert notifications, data from monitoring instrumentations, water levels, flow, or even video cameras, for example, in tunnels. And also it's important to have a preparation and emergency plans for these locations, so you're not surprised. Yeah, so the conclusion here is to avoid flooding, use a strategy including blue spot mapping and risk management with the Rimarock project, develop instructions and routines for maintenance at these locations, test the function of the drainage system is very crucial, and do maintenance where it's needed most based on the risk analysis, and upgrade and renovate where you expect to have problems. And yeah, thank you. Oh.
So thank you very much. So I hope that you all have noted some questions for the afternoon for discussion. And we come now to our last presentation before the lunch break. It's P2R2C2. It's not the little brother of R2D2, but it's pavement performance and remediation requirements following climate change. And will be presented by Andrew Dawson. And I think technique is okay. So the floor is yours.
Okay. Well, good afternoon. I think it's afternoon, yes. You're waiting for your lunch, so I'll try to keep to time. I've realised that we made a mistake in our project, and that was not to think of a nice name for our project. And the best we could come up with was P2R2C2, which might have been a star in a remote constellation. It might have been a rather cute robot, but actually it stands for Pavement Performance and Remediation Requirements Following Climate Change. And I want to say at the outset that we've very much limited ourselves to pavements, and some of the issues that have been talked about already this morning clearly have big effects on pavements. We saw the presentation from colleagues from Mexico, erosion of parts of the pavement by floodwaters. We didn't look at those type of issues in our project. We're just looking at the pavement structure and materials itself. Well, you know all about Road ERANET by now, so I didn't need to say anything about that. But we aim to look at the relevant climate changes, assess the likely consequences for road pavements of those changes, and then to propose adaptation in terms of materials, drainage and maintenance practices. We limited ourselves to a study area which was Europe north of the Alps. So for those of you from other places, I'm sorry, I don't really have much to say to you. There is some incidental information, and you'll see that on some of the plots, but we concentrated on that area. So we haven't really looked at perhaps the most extreme high temperatures, which certainly are going to be a problem for other countries. Let me talk first of all about our climate change approach. What climate change is expected? Well, that, as we've seen, depends on the assumptions we make about future emissions. I'm going to show you the same picture that you've already seen already. But we used the Intergovernmental Panels on Climate Change's assumptions A2 and B1, of which more in a second. And then, of course, we have to use those assumptions in a model of climate change. And there are probably 30 or so models of models that allow you to have a guess at future climate change. When we used two of those, we used the ones from the Hadley Centre and the Max Planck Institute. We could have used others, but those are the ones we used. Now, if we look at this figure that you've seen already with however many scenarios of future CO2 emissions on there, you'll see there's a wide range. The ones we used were A2, which is one of the higher ones, and we used B2, which is this lower one here. Not sure that I've actually got, I think there's an error somewhere, but those are the ones we used anyhow, those two indicated there. Now, you'll see that the lower of those is towards the middle, or a little lower than the middle of the possible scenarios, and the one near the maximum. Which of these is right? Well, who knows? We haven't got there yet. I very much subscribe to Pirkko's comment that she made earlier, and we'll see why in a moment. The Hadley Centre model that we adopted was the AM3H, for those of you who are climatologists here, and this is the Max Planck one we used. We then had to localise those to Europe, particularly Europe north of the Alps, and we used a climate analysis package, RCAO. This work was done by VTT in Finland with help from the University of Helsinki. Then what we did, we looked at climate over the 30-year period from 1961 to 1990, and then we also looked at it at the last 30 years of the current century. And so we got 4 sets of output produced from doing that analysis, because we had 2 scenarios we were looking at and 2 models, so we ended up with 4 possibilities. This figure seeks to identify. Someone had a pointer just now, I don't know. Was there a pointer? Yeah. Well, I can use the mouse on here, perhaps. Okay. Okay. The big button, is it? Yeah. Okay, so here up the top we've got the Hadley model. We localize it with this RCA approach. We use the 2 simulations and the control for the 1961 to 1990 situation. We compare the estimated future with the past, and we end up with a change here. And we do the same over here for the Max Planck models. Again, the 2 scenarios, compare with the control, and we get 2 change predictions. So we end up with 4 change predictions. And most of the plots I'll show you, we've averaged those to give an overall prediction. But I will talk about the uncertainty as well. This localization procedure calculates the state of the atmosphere at 100,000 grid points at 24 vertical levels. It's solved every 6 hours. This does bring us some limitations. Some people have been talking about, for example, amount of rainfall in an hour. We can't possibly calculate that with this localization technique, because it only does it every 6 hours. And we run the simulation, as I said, for 30 years. And then we've averaged the output statistics over this period. I believe some people might question the averaging here if you're looking at extremes, but I think for most of the pavement implementations that's not a big issue. And then we increase the emissions, we reanalyze over this last 30 years of this century, we compare the before and after, and we get a change. How reliable is this? Well, it depends, as I said, on the climate model and on the emission scenario. Our results probably, because we've done this averaging, are in the middle of the range of possible estimated consequences. And I have to say, as I said, I agree with Pirkko that this is increasingly looking as though it's non-conservative. In other words, that the situation will be worse than our, well, worse or better, depending on whether it's getting better or worse. I think it's looking at that as though we're not being conservative, because it depends on people. Here's the picture of India's Environment Minister, Jairam Ramesh, who's currently enjoying a short vacation in Cancun with other world leaders. And this is what he said before he went. "I don't expect any agreement at Cancun, as the developed nations have so far failed to keep their promises of funds released to the developing countries." What he's saying is there's little political will at a global scale to address the cause of a global problem. Certainly, we are engaged in our own nations at trying to address situations. We may be trying to reduce emissions in our own country, but we're not prepared to pay for other countries to do that. You don't want to tax, well, we in our own countries don't want to tax our citizens to finance India or other countries. And I don't see that going to change very quickly, if at all. All right, so with that, so allowing for the fact that we may be non-conservative, let me just give you some illustration of the variability, even with our four approaches. And our four approaches, as I said, may all be conservative anyhow. So if we look at this plot here, we've got the two Hadley models at the top, left and right, and the two Max Planck ones at the bottom, left and right. And then we've got the emission scenarios. I can't see it, you can. A2 and B2 here, from top to bottom. So this is looking at mean change in annual maximum temperature for a 30-year period by these four different approaches. And if we look at France down here, France is estimated by this combination of model and scenario is going to have an increase in its maximum temperatures of about 12 degrees over that period of 110 years. If you look up here, for example, up here, it only says it's about 5 or 6 degrees. So you've got quite a big difference in average change of temperatures depending on which one you adopt. As I said, probably we're being conservative anyhow. So just to give you some indication, and although I'm going to talk about in a second about the impact it might have on the road, just taking these four different approaches here and applying them to rutting, and we'll talk about what actually might happen. Just to give you an idea, here is a particular example. I forget exactly the road we were analysing and so on. Here is a reference performance, and then we've taken this Hadley and Max Planck A2 and B2 emissions, and we've calculated rutting by these other methods. So, yes, it gives an answer. I mean, in this case, this road wasn't particularly sensitive to rutting, but it does make a difference, as you can see, which one, which model and which scenario you adopt. So we get quite a large variation in the climate change predicted. Methods and data are uncertain. We're probably using conservative emission scenarios, and the uncertainty does affect the estimates of the impact that we have. So I recognise all those things, but now we're going to simplify it, and I'm going to assume that there's just an average, and I'm going to go on with that for the rest of my presentation. So what are the climate predictions we've looked at? Well, we looked at mean change in annual maximum temperature, so that's taking the previous one I've shown you and adding all four together and averaging them. Again, France, as you see, gets hottest, or the change in temperature in France is greatest, the peak temperature. We've looked at freeze-thaw cycles. Obviously, this is particularly a problem for countries which have cold winters. And you see here that the biggest changes are in the Alps and in the southern parts of Scandinavia and the Baltic states. I should have apologised already, and I'll do it now. For those of you who are politically sensitive, you'll notice that the University of Helsinki doesn't seem to yet receive news that there's been the breakup of the Soviet Union or of Yugoslavia. I apologise for that. So the base map on these is a rather old base map. So my apologies, but I was told it couldn't be changed, so I don't know why, but there. So I'm afraid there is, if you're from one of the Baltic states, then you can come and hit me afterwards. But they don't exist on these maps. Okay, so that's the mean number of freeze-thaw cycles per year. So we see here a significant reduction in these in the Alps and in southern Scandinavia. Not much change in northern Scandinavia. This is freeze-thaw cycles. So in northern Scandinavia, the winters are going to be shorter, but the number of freeze-thaw cycles isn't going to change very much. So it gets cold later and gets warmer earlier, but the number of cycles it goes through are not such a problem. But there is a big problem for southern Scandinavia, which has maybe in the past been used to having some frozen periods. It's going to get much more cycles in between, as we see. We also have looked at this not only just over the year, but over the seasons as well. So on the left you have December, January and February, and on the right you have March, April and May. So you can see there's quite a change here from one to the other. So for northern Scandinavia, there's an increase in freeze-thaw cycles during the winter. They haven't been so used to that before. They're going to get the weather which currently southern Scandinavia has. We looked at change in precipitation as well, and you'll see that in most places north of the Alps, there's very little change in precipitation. Slight increases in Scandinavia, and except for coastal Norway and the west coast of Scotland, which are going to get significantly wetter. Again, if you looked at the individual scenarios and analyses, you see there was a slightly more complicated picture than this averaging has brought out. But that seems to be the general picture. In fact, I say it's going to get significantly wetter. Of course, these places are the wettest already. So it may not be such a big problem to them because they already have the western coast of Norway maybe have 2 meters of rain a year at the moment. So an extra 300 millimeters may not be so noticeable in terms of total volume, whereas 300 millimeters of extra rain, where it only rains 300 millimeters at the moment, would be a big change. So it may not appear, it may not be quite as bad as that figure suggests. And of course, the rain is not going to fall uniformly, and we're going to see more intense rainstorms. We looked at change in heat sum. Now this is the number of hours when times the number of degrees, the temperature is going to be higher than 25 degrees centigrade. So we chose 25 because we're looking at Europe north of the Alps. If you look at this picture, you'll see the big changes here are going to be in southern Germany, these type of areas there. I know there's bigger numbers to the south, but so we're interested in Europe north of the Alps. So the big changes here, the Czech Republic, Slovak Republic, northern France, southern Germany, southern Poland. These are the areas which are going to see this biggest change in summer temperatures. We also did the mean change in the cold sum, and here we're talking about 0 degrees. Again, we're taking the number of degrees less than 0 times the number of hours, and we're looking at the change here. So again, the change here is most significant in the northern parts of Scandinavia. Southern Sweden and Denmark are escape, largely, and but the Baltic states clearly suffer as well, bits of Poland. We also looked at the rapid change in temperature, which might have issues for thawing. And obviously there are some issues here in the Alps and in Norway. But although we did the calculation, we didn't really do very much with that one. So let me summarise those. Clearly, temperature rise. There's going to be hotter summers, particularly in France, southern Germany, and so on. Sorry, it shouldn't say southern Slovenia, it should say Slovakia. Sorry, mistyped there, apologies. There's going to be shorter frozen periods in winter in the far north. There's going to be intermittent or no freezing in Nordic and Baltic regions. There's going to be greater precipitation in Scotland, Nordic and Baltic region and northern Poland, less precipitation in the Alps. It's going to come heavier, more intense in all regions. We expect sea level rise as well. We didn't do any calculations about that, but sea level rise is expected to go up. Again, you can read the IPCC scenarios if you like and see what's expected. And we've already seen from the swamp discussions already that we can expect more regular flooding of low points. So that's our climate inputs. What's the likely effect on the pavement? Well, higher peak temperatures in general will be good for the subgrade and the aggregate because these are geotechnical materials, so we're going to increase the suction or decrease the pore pressure by heat, so that will be good for them. There'll be more evaporation, more evapotranspiration from vegetation, and so they'll end up drier and perform better. But it's going to be challenging for the asphalt, and the areas, as we've already seen in these areas in the south of our study region, are going to be those which are going to suffer most. There's going to be not so cold winters. In the far north, we can expect reduced periods of frozen winter roads, shorter and earlier spring thaw, and more summer operation character of the pavements. That perhaps will need some adjustment in operations, but probably won't be too difficult to manage. The fact that the spring thaw will be shorter and earlier because the penetration depth of the frost over the winter didn't go down so far, that probably will be good news. But farther south, in the southern part of the Nordic and Baltic regions, we can expect more significant issues. There will be non-frozen periods during the winter. Some winters may never freeze, and there will be no real spring thaw. It'll be intermittent thaws for several times during the year, and in recent years some of that has already been seen, of course. And those will be much more difficult to manage, and we'll talk about that in a second. We looked at structural impacts of asphaltic pavements in general. We found in general that the we were a bit surprised about this, but it seems to be the most significant change will be that we'll get increases in top-down cracking. That's the area which is most concerned. Next is rutting. We might expect that with higher temperatures. And ageing will be more rapid. Roughness won't change very much. And then we're going to get better performance with bottom-up cracking and thermal cracking. So there'll generally be improvements in those areas. So it's not all bad news. Some of it's good news. This just gives you some indication here of some modelling that we did looking at cracking. In yellow, you see the original, and then we've recalculated assuming an 8-degree increase in temperature, and you can see the sort of increase in longitudinal top-down cracking that we might experience. Rain, even if we double the rainfall, doesn't seem to have a great deal of effect on that. We did quite a few analyses of pavement constructions and looking at different rainfall patterns and how that might affect the saturation of the subgrade. I said earlier that with increased temperature, we can expect drier conditions and therefore improved foundations. Of course, that's only true if the water doesn't go into the road when it rains. And so we needed to look at the drainage conditions here. We're not now talking about surface drainage in order to keep water off the carriageway for driving conditions, as Swamp has been looking at, but looking now at the subsurface drainage and making sure that the rain that does fall on top of the roads in these more intense events doesn't actually get into the road construction and cause softening. So we've done a number of analyses like this, and these indicate the sensitivity that there is of the construction to the amount of water which gets into the pavement. And with more intense rainfall, this is going to be something we're going to have to look more seriously at. Because softened subgrades lead to pavement distress in more general terms. A consequence we believe is that subsurface drains will need extra capacity and maintenance. Here is a so-called subsurface drain alongside the road. You can see it's become surcharged because the drain isn't working anymore, and it's become a surface drain. Now, clearly that's feeding water into the pavement, not taking it out. All right, it's a nice picture, and I thank my colleague in Finland who gave that to me. But this is the sort of issue we're going to have to think of with subsurface drains. They've got to take the water out. And if it's difficult, as we've heard from the Swamp project, to look after the surface drainage system, which we can see, how much more difficult is it to persuade there to be good maintenance of the subsurface drainage system, which we don't see? So this, I think, is a real issue for us. There are two special cases, which I'll just briefly touch on, about low points, or blue spots, I guess. I must learn to use that phrase, and those by the sea. There will be higher water tables, and therefore if the general water table is high, there will be considerable loss of support 24/7, not just when there's heavy rainfall. And those may need to be specially addressed. So let me summarise the impacts. There will be, broadly speaking, hotter asphalt surfacing, giving rise to greater top-down cracking and rutting. In other ways, the impacts will generally be neutral or improved. There will be less cold winters, which will have both a benefit and a problem in the far north. There are benefits in terms of a less severe spring thaw and a longer summer, but a problem in that a shorter frozen winter, and often forestry, for example, uses the frozen winter to carry their heaviest loads out of the forest, so that could be an issue. Farther south, there will be intermittent or no frozen winter, which will increasingly make unsealed pavements less acceptable in these areas because they won't be able to handle with that intermittent freezing and thawing all winter long. Good news is that where thick embankments are built on major roads in Nordic countries at the moment to prevent frost penetration, then in the longer term it will be possible to build those embankments a little thinner because there won't be such great frost penetration. Elsewhere, road structures that are already in a fair or good condition should remain okay or get a little better because of equal or better support conditions. With the heavier rainfall, those areas which have extra rain, because it's going to fall largely as heavier rainfall, then it should run off more readily. Won't have so much time to soak in because it's going to be less frequent. So again, that will be lead to a general improvement. There will be wetter surfacing during and after rain, and it will be at higher temperatures, which will give rise to some stripping issues of the asphalt. But there's going to be drainage challenges, as we've seen, and if these aren't addressed, then the benefits that I've just listed won't actually be achieved in practice. So we've got high water tables in blue spots, or close to the sea, and so in those areas we're going to have to think about special measures to address those. So overall, I would say how important is it? Mostly, I'm being very general here, mostly it's non-critical. Mostly better or no worse subgrade support, and because we typically design pavements for maybe a 20-year life cycle, something like that, then we can make our adaptation during our normal maintenance cycle. pavement replacements is going to be at a faster rate than any temporarily significant change in the climate. We can change the material formulation when we next reconstruct at minor cost differential. There could be problems for so-called perpetual pavements. I don't like the word myself, but I know it's become popular. I don't think anything is perpetual in life. They may need to have modified resurfacings because they've been designed for one particular climate and now will have to operate in another. There are some critical exceptions, though, and we've already seen about unsealed pavements in these Nordic and Baltic regions, which are going to face too frequent thaw weakening in future. And low-lying sections which will likely have significantly softened support conditions. And we've seen that malfunctioning drains will be more damaging to pavement condition in future. So we really do need to think about our subsurface drainage systems and make sure they work. And if I was guessing at the beginning about what climate change will actually be achieved, and guessing that the world's response to global climate change will be a lot of hot air and not much else, then I would also guess actually that pavement engineers will not do much with their subsurface drainage systems. Everybody in pavement engineering knows that subsurface drainage systems are important. They've known it for a long time and they don't do anything about it. So past history, I would guess that not much will happen in the future. So I think actually, because people don't do anything, actually pavements will generally get worse, even though in principle they should get better. What should we do? Well, we should act now in updating standards for new climate in pavement design, temperatures and so on. We should develop our drainage designs for higher flows, and we need to look at return periods. We need self-cleaning designs. Self-cleansing designs should be developed in order that our poor maintenance record actually isn't too much of a tragedy for us. And we need to make our subsurface drains easily inspectable and maintainable. So we need to think about those in order that we can overcome this problem. I suggest that Nordic and Baltic regions particularly give careful thought to a programme of stabilisation of unsealed pavements in order to adapt to the likely change in climate which is coming their ways. And for those roads, these blue spots, I'm thinking about the subgrade. You were thinking about the flooding of them, but I think they should be raised, therefore, so that the subgrade is drier and gives good support. We need to pay particular attention to crack sealing on the poorer performing pavements to try and keep the water out. Act later and don't panic in a few areas. Include different but not novel materials. They're routine materials, you're just not using them at the moment, next time the road's constructed. And I want to say that I think that user and funder demands will change much more than the climate. So actually I think our pavements are going to suffer much more from other things than climate. They're going to change faster and they're going to change more significantly. For example, if you were standing here in 1910 rather than 2010, just think of the changes there's been to pavements over the last 100 years. And they're nothing to do with climate, but they're to do with vehicles, they're to do with population, they're to do with politics, they're to do with our society's changes. And I think those changes are going to be very, very much more significant on our spending needs than climate's going to be. Demographic changes will be high, and some of those are going to be driven by climate change. It will get less popular to live in low-lying areas, for example. It will get less popular to live near the sea. So we can expect people to move, we can expect the roads to move, and the traffic demands on those roads to change. Let me thank my colleagues in this project, in ZAG in Slovenia, in VTT in Finland, and SINTEF in Norway. And let me point out to you that there is a brochure. I hope most of you have picked up a copy. There are some on the table at the back, and there's a copy of this poster produced as a poster and pinned up. So I brought one for everybody here. So, and on it here is our website, and all the reports and other things can be downloaded from the website. Thank you very much.
So, thank you. Thank you very much, and thank you also all the other speakers for keeping time and for your interesting results. I think you have enough questions for the workshops after the lunch break. Before we go to the lunch break, I have some announcements to make. One, there will be a CD with the presentations that we have seen today, and I should check how many of you would be interested to have such a CD. If you could raise your hand if you're interested. So I would say it's mostly everybody, because the question was if it's 10, 20 or 100, but thank you for that. Yeah, lunch break will be outside on the left. There you will find the food. Lunch break stops at 1:45. We will continue at 1:45 in the two workshops directly. So there is Rimorock and Swamp, workshop 1, those with the green dots. And we have workshop number 2, Urban and P2R2C2 with the black dots. As far as I know, it will be in this room that will be separated, or there will be 2 rooms? Yeah, you will find it here, workshop 1 and workshop 2. After that, there will be the coffee break at 3:15, half an hour, and then there is the final plenary discussion moderated by Steve Phillips. But now, enjoy the meal at the lunch break. Yeah. Something more?
Yeah, something more. Sorry.
Okay.
We need to divide the room, and therefore you need to take all your things with you, because otherwise you will have a little climate event here, like a thunderstorm. So please take all your things from the tables, and if you have luggage to store, behind this wall there's another room, and you can put your luggage there. The access is through the entrance hall. Thank you very much.
But now lunch break.